the 5 types of chemical reactions. I made you a handy dandy note sheet. It's called Identifying Reaction Types, so you want to turn to that in your packet. 5 types of reaction are synthesis, decomposition, combustion, single displacement, and double displacement. First of all, let's talk about how we know that a chemical reaction is actually taking place. So let's think about that. We'll relate it to something that everybody's familiar with, and that's like cooking and taking stuff out of the fridge and eating it, you know? So let's say you went to go grab either a glass of milk or something like that, and it was at the expiration date, and you're like, geez, I wonder if this is still good or not. What would you do to try to decide if it was good? Yes. You would smell it, right? Because odor change is an example of an indication that a chemical reaction has taken place. Same thing with color change. Let's just say you're making a grilled cheese. You know, when you're flipping it over, you try to get it that perfect color because you know it'll be cooked exactly the way you like it. Some people like them cooked more than others, right? I like mine a little darker golden than some people. And that's a color change. You have to be careful with color change, though, because if you're going to make yourself a pitcher of Kool-Aid, you've got your pitcher that's filled with water and it's clear, colorless. And then you put the Kool-Aid mixture in. Let's just say you're making the tropical punch. When you put that mixture in, the water is going to turn bright red. But that's not really a color change because the red was in the powder and it just spread out. So that's not an example of a color change, and it's not the example of a chemical reaction taking place. Another example is, let's say you had some blue Kool-Aid and some red Kool-Aid, and you decided to get a little creative and mix them together. You would end up with purple Kool-Aid. That's not a color change either. That's just you're seeing both colors at the same time. Formation of a gas or a solid. You'd probably know that if you took the milk out and it had that solid piece at the bottom, you'd be like, yeah, I'm not drinking that. Or if it was bubbling, you would know that that's a bad sign. Difficult to reverse. So once you burn that grilled cheese, you know you can't unburn it. Or if you think of an egg, the egg white is clear, then you cook it and it becomes white. You know you can't uncook an egg. And the release or absorption of energy. Remember when we did our whoosh bottle over there? You knew that was a chemical reaction because you saw lots of energy being released, right? So that's another example of an indicator that a chemical reaction has taken place. So now let's go through our individual types of reactions. You probably want to get like a highlighter or something out, or at least a pencil to make stars by. How are we going to decide what kind of chemical reaction we are looking at? A synthesis reaction is a combination of 2 or more simple substances combining to form a more complex substance. So 2 elements on the reactant side is an indication that you have a synthesis reaction. So how we identify a synthesis reaction, and this is what you want to highlight there, is that there's one product. So if you have element on the reactant side, that's a synthesis reaction. One product is a dead giveaway that you have a synthesis reaction. Here's an example of a synthesis reaction where you have element on the reactant side, and then on the product side, you have a compound. Remember, oxygen is O2, so that is what elemental oxygen looks like. You're never going to have O, it's always going to be O2. And of course, we have to balance it. Here is a molecular view of a synthesis reaction. This would be if we took elemental potassium and added it to elemental chlorine to produce potassium chloride. Here's just a couple other examples of synthesis reactions. Next is decomposition reactions. Fortunately, synthesis and decomposition mean the same in chemistry class as they do pretty much everywhere else. So decomposition is the breaking down. So breaking down of large complex molecules into smaller, simpler molecules or elements. How we identify a decomposition reaction is that there is one reactant. So that's what you want to highlight, is one reactant. Here is a molecular view of a decomposition reaction. This is the decomposition of the ionic compound Mercury 2 oxide. You add heat and it will decompose into elemental mercury, which is actually a liquid, and oxygen gas. Here's a particle picture of the decomposition of hydrogen peroxide. This is the reaction that we did with the elephant's toothpaste. And if you remember at the beginning of the year, the Chem-Genie, that was also decomposition of hydrogen peroxide. Remember, we added a catalyst to that. So that was the catalytic decomposition of hydrogen peroxide. So pretty complicated what we did with that elephant's toothpaste, huh? Always have to remember to balance it. A decomposition reaction always has one reactant. Next is a combustion reaction. This is more commonly known as burning. So you've probably been using that term your entire life and maybe never realized that this is an actual chemistry term, is burning. It is identified by the release of heat. Does anybody know what a reaction is called that releases heat? The word is exothermic. You'll see in your notes off to the side, they'll say that combustion reactions are always exothermic. For combustion reactions, you need three things. You need fuel, you need oxygen, and you need heat. So let's review that. When we did our combustion reaction, that was our whoosh bottle. Remember, I had the isopropyl alcohol in the container, and you probably have isopropyl alcohol at home. It's never going to start on fire like that. It wasn't until I dropped that lit splint into it that it started to react. That's the amount of energy or heat that I needed to add to get the reaction started. That's called activation energy. So it'll never start to react on its own, but you noticed once I added that energy, it reacted pretty dramatically, didn't it? And you knew that that was a chemical reaction because you saw the release of heat. So what you want to highlight in combustion reactions is just highlight that oxygen in the reactant side of those example reactions. Oxygen has to be one of the reactants as O2, not part of a different compound or anything. It has to be elemental oxygen standing by itself as O2. Here is an example of a combustion of a hydrocarbon. Remember, when you combust a hydrocarbon is a compound that has hydrogen and carbon in it. Combustion of a hydrocarbon always results in carbon dioxide and water. If you remember, we talked extensively about carbon dioxide the other day, and this is one of the reasons why carbon dioxide is building up in the atmosphere, is because every combustion reaction that we do results in carbon dioxide being produced. Here's some other examples of combustion reactions that aren't hydrocarbons that can happen also. Remember we talked about how oxygen is everywhere? Well, it loves to react with things, and that's why many, many compounds contain oxygen. You can see that this list of commercial applications that we burn things or combust things they all produce what's called greenhouse gases or pollution gases. So you can see some examples of things that produce greenhouse gases. Now, I want to clarify for you, though, that's the complete combustion. The complete combustion of hydrocarbon produces carbon dioxide and water. You have to be careful, though, when you're doing combustion reactions, you must make sure that those reactions have enough oxygen. If you don't learn anything in chemistry class, you definitely want to learn that combustion reactions need to have excess oxygen or plenty of oxygen. Otherwise, you're going to produce carbon monoxide. If you don't have enough oxygen, it'll be called incomplete combustion, and you'll produce carbon monoxide, and it is fatal. So they theorize. Have you ever heard the story of Edgar Allan Poe and how he walked out of a bar, sat down on a bench, and just died, and they didn't know what he died from? They go back and they like to theorize that part of his problem may have been carbon monoxide poisoning, which they probably couldn't identify way back then. So if you're ever in Baltimore, the bar that he walked out of is still there. You can go see the bench, the very bench that he walked out of that bar and sat down and died on. Next is single displacement reaction. How you identify a single displacement reaction is that you have, this one's not as easy, so there's not going to be that telltale sign. You have element and compound on the reactant side, and then you have a different element and compound on the product side. So somebody's single on the reactant side, somebody else is single on the product side. So in your pink packet, I want you to turn to the page that says activity series of elements. It's right next to your off-ball diagram. So in chemistry class, in chemical reactions, everybody wants to be part of a compound. So A would love to kick B out. The only way that A can kick B out is if it's a more active metal. So you see at the top, our most reactive metal on our activity series is lithium. And then you go down and closer to the bottom, it's actually hydrogen, because this is hydrogen as a cation. And then as you go down, look at underneath hydrogen. You've got some of your metals that we know are less reactive. So these metals up at top, you might not have even known that they were metals, right? Did you know that before chemistry class? Did you know that lithium, potassium, calcium, sodium were metals? The reason you probably didn't know that is because you're not going to find any of these. These are too reactive. You're not going to find any of them alone in nature. So you've never seen any of those metals because they're always chemically combined with somebody else. Then you get down to the bottom. You know, as you get to the middle, you've seen aluminum, you've seen zinc, you've seen iron, you've seen nickel, you've seen tin, and you've seen lead. Obviously, copper, silver, and gold. Has everybody here seen Mercury before?
Isn't it that like silvery thing?
Yeah, it's like a silvery, but it's a liquid. It's like a liquid metal. They used to put them in thermometers, but then they decided that playing with mercury wasn't a good idea. So you may still have a mercury thermometer around your house. It's actually a pretty cool liquid to kind of check out. So these are less reactive metals. That's why they can come by themselves. You've seen aluminum foil. Believe it or not, most of the coins that you have are actually mostly zinc. So if you think that pennies are copper, we are going to do a lab where you'll get to see what pennies are actually made of. Iron, you may or may not have seen iron by itself. It's usually part of what's called an alloy, which is a mixture of metals, such as steel. Tin is what they make like Altoid containers out of. Lead, if you're a fisherman, they make lead weights. They also make BBs out of them. And then obviously, you know, copper, silver, and gold. Silver and gold are so non-reactive, you can actually wear them as jewelry. So here's a molecular view of a single displacement reaction where lithium is kicking hydrogen out of a compound to become lithium oxide and releasing hydrogen gas. Here's the single displacement of zinc kicking hydrogen out of a compound. Notice you can identify it as zinc is by himself or single on the reactant side, and he's in a compound on the product side. Hydrogen's in a compound on the reactant side, and he's single on the product side. So here's what it looks like. Make sure that if it's a metal trying to get to be part of a compound, that the metal's kicking the metal out. Cations replace cations. If it's an anion trying to get into the compound, if it's a non-metal trying to get into the compound, it will kick out the anion or the non-metal at the end of the compound. So here's the activity series. Notice at the top, lithium is the most reactive, and at the bottom is your least reactive metals. So if a more reactive metal is already part of the compound, it's not going to react. You would write no reaction. Okay, our last type of reaction is double displacement. This is the reaction of two compounds. We did a couple of these the other day. So they're going to switch spots. When they switch spots, they will trade partners. But metals can't be with metals. Cations cannot be with cations. So it's going to be the metal will grab the other anion on the product side. So make sure that you've got compound, compound to identify on each side. Compound, compound on the reactant side. Compound, compound on the product side. That's going to give you the telltale clues that this is a double displacement reaction. Now we have a couple different kinds of double displacement reaction. You might want to write this down. One of them is when you put together two compounds that are both aqueous, meaning they're both dissolved in water, and you get a precipitate formed. So you have to identify it first that it's double displacement. That'll be compound, compound on the reactant side, compound, compound on the product side. You have to recognize that both of the compounds on the reactant side are aqueous, and one of them's a solid on the product side. That's a precipitate. That would be a precipitate reaction. You could also produce a gas. And the last one says a pH change occurs. What that means is if you have, remember our example from yesterday where we had a strong acid, sulfuric acid, and we added it to a strong base, sodium hydroxide. Sulfuric acid is a strong, dangerous compound. If you poured it on yourself, it would eat through your skin. Sodium hydroxide is a strong, dangerous base that eats through fat and hair. That's why it's the active ingredient in drain cleaner. You put them together and they form a salt and water. So how you would identify a acid-base neutralization reaction is that you have compound, compound on the reactant side, compound, compound on the product side, and one of those products is water. So you're going to have an acid and a base on the reactant side, and you're going to have water on the product side. That's how you'd identify a neutralization reaction. When it says a pH change occurs, that means that bases have a high pH around 14, acids have a low pH around 0, and when you put them together, they will neutralize each other and they'll have a neutral pH of about 7. This is what's called a solubility table. So in your pink packet, it's right above your activity series. Let's go ahead and see if we can figure out how to read this. So let's pick a compound that is pretty known to us. At the bottom here, you're going to find the cation sodium, Na+, and you're going to run your finger over to the chloride ion, which is 2 columns in. You see how it says big S? Big S stands for soluble. This may be confusing because you'd think, well, big S probably stands for solid, right? It stands for soluble. So down here at the bottom in your key, write soluble in cold water, then you write AQ. So soluble means it will dissolve. So right next to the big S, write AQ. Now let's go to the little s. Find mercury 2. So mercury plus 2 in the cations. It's 4 cations down. Then run your finger over to bromine. Do you see that has a little s, a lowercase s? That means slightly soluble. For our purposes, we're going to write S for solid. We're not going to worry about slightly soluble in this class. So write S for solid. Let's do the last one, which is I for insoluble. Let's find silver, which is at the top of the list of cations, and run your finger over to sulfate. See how it says I? I stands for insoluble, so you would write S for solid. That is an insoluble salt. We're not going to worry about decomposes. What that means is that it won't dissolve or stay as a solid. It's going to do something else. So we're just not going to worry about decomposes in this class either. Okay, here's our summary. Our 5 types of reactions are synthesis, decomposition, combustion, single replacement or single displacement, double replacement or double displacement. Synthesis can also be thought of as a combination reaction, you might hear it called. That's when you have 2 elements on the reactant side. You will identify it because it has 1 compound on the product side. So it only has 1 product. Decomposition, you're going to recognize as having 1 compound on the reactant side, so it only has 1 reactant. And then it'll have 2 or more elements or compounds on the product side. Combustion, we identify because it has oxygen as a reactant. Single replacement has 1 guy who's single and 1 guy who's in a compound on both sides. Double displacement has 2 compounds on the reactants, 2 compounds on the products.